All right, so this is section 4.6, and in this section, we will be looking at solving exponential and log equations. The first tool that we have here and the last tool are tools that we use on exponential equations, and these middle two are tools that we use on log equations. And so we're going to be looking at exponential equations first. So we're going to be looking at these two tools here. And if we were kind of trying to prioritize which tool we would rather use, we would rather use this first one. If it's possible for us to write this expression here with a base here and a base here that are the same number, then I can set my exponents equal to each other. That's kind of our plan A. But if that's not possible, then the other tool we can use is that we can take the log or the natural log of both sides of our equation. So looking at our first few examples here, the first example we have 5 to the power of 3x minus 6, and then 125 on this side. If it's possible for me to rewrite 5 and 125 as the same number to some power, that would be ideal. Now, 5 can't be rewritten as anything smaller, but 125 can be written as 5 cubed. And that is the same base as the other side. So I have 5 to the power of 3x minus 6. And now that those bases are the same, those exponents are also equal to each other. So now I can set 3x minus 6 equal to 3. And then I can add 6 to both sides. And I have 3x equals 9, so x equals 3. And so that is the kind of plan A, most ideal way to solve these exponential equations. In the next example here, I have 4 and 8 as my bases, and there's no way for me to write 8 as 4 to some power. 4 to the first power is 4, 4 squared is 16, so already too low and then too high. But it is possible for me to rewrite both of these numbers as a number even smaller than what we see here. 4 is the same thing as 2 squared, and 8 is the same thing as 2 cubed. So I replaced 4 with 2 squared, and then I can bring down the exponent I had before, x minus 3. And then here I had 8, and that was to the power of x plus 2. And these exponents here, this 3 and x plus 2, get multiplied, and then the same thing here. So this becomes 2 to the power of 3x plus 6, and 2 to the power of 2x minus 6. And now those bases are the same, so that means my exponents are also equal to each other. So 3x plus 6 is equal to 2x minus 6. I can subtract 2x from both sides. I can subtract 6 from both sides. That cancels and that cancels. And then I'm left with x is equal to negative 12. All right. The next one, we have 5 to the power of x equals 134. Now, 5 can't be rewritten as anything smaller than that, and 134 cannot be written as 5 to some power. So this is now no longer our plan A. This is now where we're going to have to take the log of both sides. Now, you can use a regular logarithm or you can use a natural logarithm on this problem. I'm going to go ahead and use a regular common logarithm. And this x is going to come out front here, and I have x log 5 is equal to log of 134. And our goal here is to solve for x. That's been our goal in all of these problems so far. So log 5 is just a number. If you type that in your calculator, you get a decimal. And log of 134 is also just a number. If you type that in your calculator, you get a decimal. So I have x times a number here, and to get that off, I can divide both sides by log 5. So I have x is equal to log of 134 over log of 5. I cannot combine this. This is not equal to log of 134 over 5. I can't put that inside a single logarithm. But what I can do is leave it exactly like what I have right there, and I can go ahead and type that in my calculator and get an approximation. So typing that into my calculator, I have log of 134 over log of 5, and I get approximately 3.04. So on a quiz or a test, I would want to see this exact answer here, and then I'd also want to see this decimal approximation. In the next example here, we have 10 to the power of x and 8,000 on the other side. There's no way for me to write these numbers as the same base, so I can't use my plan A. I have to go with plan B. And I could take the log or the natural log of both sides, but because I have a base 10 right here, it makes more sense for us to use a logarithm, a common logarithm. So taking log of 10, that x can come out front using those expanding rules that we used in the previous section. And log of 10 equals log of 8,000. And the base of a common logarithm is 10. And if those base and this number are the same, then that means that this piece here is equal to 1. So I already have x by itself. X is equal to log of 8,000. And I can, again, plug that in my calculator and get an approximation, and that would be 3.9. In the next example, before I can start deciding whether I can use a logarithm or a natural logarithm or whether I can rewrite my bases, I need to get this exponential expression by itself. So I'm going to add 3 to both sides. And then I have 40e to the 6x is equal to 240. And I can divide both sides by 40. And I get e to the 6x is equal to 6. And now I can go ahead and start to think what method I'm going to use here. And in this case, because I have a base of e, it makes more sense for us to take the natural log of both sides instead of a common logarithm. So I'm going to use natural log here. And that 6x can come out front. So I have 6x ln of e is equal to ln of 6. And remember that if you have natural log of e, that base is also e. And like the previous example, that means this is equal to 1. So I already have 6x by itself. This whole piece here is just equal to 1. And so 6x is equal to ln of 6. I can divide by 6. And sometimes I'll see students do this, and those cannot be canceled out. This 6 is inside of this logarithm. It can't come out. This 6 is not inside a logarithm, and so it can't be reduced with that 6. So my exact answer would be x equals ln of 6 over 6. And then I can type that into my calculator, and I get 0.299. All right, on the next page, we have another exponential equation, and this one is going to be kind of interesting. There's going to be a lot of moving parts to it here because we have kind of larger exponents here. So I cannot rewrite my bases as the same number, so I'm going to have to take the log or natural log of both sides. It doesn't matter which one I use. I don't have a base of e and I don't have a base of 10, so it doesn't really matter which one I use. I'm going to go ahead and take the natural log again. So now I'm moving those exponents out front, and it's really important that you put parentheses around those exponents. So I have x minus 2 ln of 5 is equal to 2x plus 3 ln of 4. And then I can distribute that natural log onto both of those terms. So I have x ln of 5 minus 2 ln of 5 equals 2x ln of 4 plus 3 ln of 4. And what I have here is an equation where I have terms that have an x on them and terms that are just a number. So if I had an equation, let's say something like 5x plus 4 equals 2x plus 7, I would try to get all the numbers on one side and all the x's on the other side. But that's exactly what I have here. I have a term with an x and another term with an x and a term that's a number and another term that's a number. So these two don't have an x. These two terms have an x. And so I want these terms on the same side and these terms on the other side. So what I'm going to do then is I'm going to subtract this term over here, and I'm going to add this term over here. So plus 2 ln of 5 plus 2 ln of 5 minus 2x ln 4 minus 2x ln 4. And these are different natural logs. The number inside this natural log is a 5. The one inside this one is a 4. So they cannot be combined. On the right-hand side of my equation now, I have 3 ln 4 plus 2 ln 5. And on the left-hand side, I have x ln 5 minus 2x ln 4. And I notice here that I have an x on both of these terms, and so I'm going to factor that out. And then what I have left in parentheses is the rest of that. Natural log of 5 minus 2 ln of 4 equals 3 ln of 4 plus 2 ln of 5. And now I have x times this number equals this number. So I'm going to divide that number over. So this is kind of like if I had 5x equals 15. I would divide both sides by 5. And so this piece here is like that 5. I can go ahead and divide both sides of my equation by that number. So x is equal to 3 ln 4 plus 2 ln 5 over ln 5 minus 2 ln 4. And that's my exact answer. So when I type this in my calculator, you need to put a set of parentheses around this entire numerator and a set of parentheses around the entire denominator, and then a division symbol in between. Otherwise, it will not calculate your decimal correctly. And when we plug this into our calculator, we end up with approximately negative 6.34. So there is my exact answer and my rounded answer. So this next example looks a little bit different. We have two terms with an e on it, and then we have 7 here. And this is e to the x, and this is e to the 2x. I'm going to do a substitution here. I'm going to let e to the x equal u. And this is called a u substitution. When you're in calculus, you'll do a lot of these. And if I square both sides, then this becomes e to the 2x, and that would become u squared. So e to the 2x is u squared minus 8u plus 7 equals 0. And this is a quadratic equation, just like we've been solving all throughout this course. So a times c is 7. My b value is negative 8. Negative 1 and negative 7 multiply to 7 and add to negative 8. So I have u minus 1 and u minus 7 equals 0. So u equals 1 and u equals 7. So I can now solve both of those equations, plugging back in for what u is actually equal to, because what I'm actually interested in is e to the x. So e to the x equals 1 and e to the x equals 7. Well, I can take the natural log of both sides of these equations. And when I do that, I have ln and ln. And ln of e to the x is just x. And natural log of 1 is 0. And then over here, when I take the natural log of both sides, I can bring my x out front. And then I have x ln of e equals ln of 7. And like we saw over here, natural log of e is just equal to 1. So x is equal to ln of 7. And I could come up with an approximation for that. That would be 1.95. So those are all of the exponential equations. Now, these last 4 examples here are log equations. And so flipping back to the previous page, we're going to be using numbers 2 and 3. So for number 2, I have log base b of m equals log base b of n. This is kind of like our plan A for exponential equations. This is our plan A for log equations. If I can write each side as a single logarithm with the same base, then I can set the insides equal to each other. If that's not possible, if we have even one term that does not have a logarithm on it, that's just a constant, then I have to get one logarithm on one side and use the snail rule to rewrite it in exponential form. So let's see how those play out in actual examples here. In this first example here, I have a logarithm on this side and just a constant on this side. So I cannot do plan A here. I have to use the snail rule here. I have a single logarithm already by itself and a number on the other side. So using the snail rule to rewrite this as an exponential equation, I have 2 to the power of 3 is equal to x minus 4. Well, 2 to the power of 3 is 8 and x minus 4. And if I add 4 to both sides, I get x is equal to 12. Now with log equations, we have to be careful and we have to make sure that we check our answers because log equations don't have all real numbers as their domain. We have to make sure that what we get as our answer when I plug it in my equation does not give me a negative inside my logarithm. It's okay to get a negative answer as long as when you plug it back in here, what you get inside your logarithm is not negative. So 12 minus 4 is 8. That's a positive number, so this is okay. In the next example, we have 4 times natural log of 3x equals 8. And before I can use the snail rule, I need to divide this 4 off this side. So dividing both sides by 4, I have ln of 3x is equal to 2. And remember that the base of natural log is e. So I have e to the power of 2 equals 3x. And then if I divide both sides by 3, x is equal to e squared over 3. And I can plug that in my calculator and get an approximation for that, and that is 2.46. And again, I need to check my answer. So if I plug this positive number in here, 2.46 times 3, that's a positive number, and so that's okay. There's nothing wrong with plugging that in. All right, the next equation does not have a single logarithm on this side, but it does have a term without a logarithm, so I still have to use that same process. But I need to condense this before I can do that. I can't use the snail rule when there's 2 different logarithms. I need a single logarithm on this side. So log base 10 of x plus log base 10 of x minus 3. Multiplication condenses, addition condenses to multiplication. So I have log of x times x minus 3 is equal to 1. And I can go ahead and multiply that. I have log of x squared minus 3x is equal to 1. And then my base here is 10. If you don't see a number there, we assume 10 if it's a logarithm. So 10 to the power of 1 equals x squared minus 3. So 10 to the power of 1 is just 10 equals x squared minus 3x. I can set that equal to 0, and I have x squared minus 3x minus 10 equals 0. And that's a quadratic equation that we can solve. Negative 10 and negative 3, negative 5 and positive 2. And that gives me x minus 5 and x plus 2. And x is equal to 5 and x is equal to negative 2. And once I get down to this step here, I need to check those answers. Plugging 5 in, 5 is a positive number in here, and that's fine. 5 minus 3 is 2, that's fine. So 5 works. When I plug in negative 2 here, negative 2 is a negative inside that logarithm. So that cannot be a solution. That number would have to be okay in all of the logarithms in this problem. And even having one of them that doesn't work means I cannot include that in my answer. So my only answer here is x minus 5. And the problem here is not the fact that 2 is negative, it's that when we plug it in, it produces a negative inside the logarithm. All right, one more example. And we have here natural log of x plus 2 minus natural log of 4x plus 3, and then equals the natural log of 1 over x. Every single term has a logarithm. So this is kind of our plan A. This is what we want to see happen. I need to condense this side and write it as a single logarithm, and I already have a single logarithm on this side. So this becomes natural log of subtraction condenses to division, so x plus 2 divided by 4x plus 3 equals natural log of 1 over x. And then this is equal to this. So I have x plus 2 is over 4x plus 3 is equal to 1 over x. And then I can cross multiply. X plus 2 times x gives me x times x plus 2 is equal to 1 times 4x plus 3. X squared plus 2x equals 4x plus 3. And I can subtract 4x and subtract 3 from both sides. And I get x squared minus 2x minus 3 equals 0. And I can go ahead and factor and solve. So -3 and -2, -3 and +1, multiply to -3 and add to -2. So x minus 3 and x plus 1 equals 0, x equals 3, and x equals -1. And once I get to that point, I need to go ahead and check them. So when I plug in 3 plus 2, that's positive. 3 times 4 is 12, plus 3 is 15, that's positive. 1 divided by 3, that's a positive number. So this one is okay. If I plug in -1 plus 2, that's a positive 1, that's okay. -1 times 4 is -4. -4 plus 3 is -1. So even though this one was okay, this one wasn't, and so this cannot be an answer. Again, it is okay to get a negative answer here as long as when you plug it in, it doesn't produce a negative inside the parentheses. So if this one hadn't been here, that -1 plus 2 was okay here. It also would have failed here, but as long as we get a negative here that when we plug it into all of them, it doesn't give us a negative inside the logarithm, it would be okay. And that's the last example in this section, and that's the end of section 4.6.